Hi everyone. My name is Nicolette, and today we're going to help you guys cover solubility equilibrium. All right. So specifically, what we're going to do today is we're going to look at complex ion equilibria. So to solve equations with complex ions, we have to acknowledge what they're made of and why they're special. So a complex ion, or otherwise known as a coordination complex, it consists of ligands surrounding a transition metal cation. In this case, we have NH3, two NH3s surrounding a silver cation with an overall positive charge. So they'll often look like this, where you have your metal in the center and your ligands on either side. All right. So we have to know this is also a part of what we're learning is with our Lewis acids and bases, and ligands act as Lewis bases, which means in our complex ions. So that means that they donate a pair of electrons to the central atom, which also explains why they are together. So the equilibrium constant for reaction between the metal ion and the ligands mentioned above is represented by Kf, which is a formation constant, which is the concentration of the products over the concentration of reactants, much of like how we have already been doing for most of this semester. We can look at this reaction also in the reverse direction. It's represented by Kd, which is the dissociation constant. So this is equal to 1 over Kf. So you can do this either way, and today we're going to be focusing on the forward reaction in our example. All right, so here's some good steps to follow. So first, we have to identify the reaction taking place. This is very important because it will define everything that we do afterwards. Like I said, so after that, we will create an isotable of the reaction that we see occurring between this central atom and the ligands and whatever is occurring. So, and from there, we will substitute values from the above step to the Kf or Kd expression, depending on whether we are looking at the dissociation or the formation of our complex ion. Then we combine our like terms, and we use X relations in the above isotables to calculate all the equilibrium calculations that we need. So let's try an example. So here's our question. How many moles of silver bromide can we dissolve in a liter of 1 molar NH3? Our KSP is for silver bromide is given in 5 times 10 to the negative 13 moles, and our KF is given as AgNH3 to the 2, the positive ion, and this is a concentration of 1.6 times 10 to the 7th moles. So first off, we have to understand the reaction occurring here. So in dissolving silver bromide, we have our silver bromide as a solid, and it goes into our ions of our silver ions alone and our bromide ions alone. So in dissolving, and then we have to look at the context, because remember, it's dissolving in NH3. So in dissolving NH3, we have our silver ions and our 2 NH3. Sorry, I missed this right here, which results in the formation of our complex ion that we are dealing with, plus our bromide, which will eventually have our addition of the bromide ion. So if we combine these two things that are happening right here, we can look at our total reaction that's happening. So we have our solid silver bromide that we have placed in our NH3 formula. We have balanced it. We have added the 2 here. And in the process, we are creating the mentioned complex ion, which is AgNH32, which is exactly what we need, and our bromide ion. So also, we have to keep in mind that our KSP is our silver concentration ions with our bromide concentration ions. All right,